Hello and welcome to one more day of the Advent of Code 2022. Today, day 7. As always, we're going to read the statement, which I haven't read yet. Then I'm going to code the solution till we get the gold stars. And finally, we'll do some refactoring and a recap of the lessons we learned through the process. Let's start as usual by reading the input. Okay, today the input seems to be a little bit complicated. Okay, CD, LS, there. This looks like some kind of input from some shell in. Let's grab the $sign. So, I guess that's how it. I wanted to see what kind of commands we have. We have ls and we have cd. So it's always ls or cd. Okay, let's go and read the statement. Or let's see what is asked from us. Find all of the directories with a total size of at most 100,000. What is the sum of the total sizes of those directories? Okay. So the device the elves gave you has a problem with more than just its communication system. You try to run a system update. No space left on device. Okay. Perhaps you can delete some files to make space for the update. You browse around the file system to assess the situation and save the resulting terminal output, your puzzle input. For example, this. So here we have in directory / which is the root, I guess, ls. So there is directory A and these two files, I guess. So this is a directory and this is a file with a given size. The file system consists of a tree of files, plain data, and directories which can contain other directories or files. The outermost directory is called root, /. Within the terminal output, lines that begin with $, are commands you executed. Okay, you change directory, you list, this is a file, this is a directory. Okay, it makes sense. Let's read the input again. We start here, we do some ls, and then we change there, and then we change up. Okay, I think I know more or less how to start to code this problem. So we could start with all the. Maybe we should start by reading all of the input, right? Or maybe not. What do we prefer? Should we read all of the input before, or should we just do it as in one passing? Maybe we should do it in one passing, or maybe not. Okay. CD, 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 CD. Let's read all the lines first. So lines equals open 7.in.read.split lines. I'm going to try to do it all in one passing. Let's see if that works. So we have the lines, so we could have the let's have a function which is process, which will have an index, so what line we are processing right now. Then it will have the tree structure, which will be some kind of dictionary. And then maybe that's it. So what we're going to do is we're going to process lines. And then what we need to do down here is find all the directories with a total size of at most 1,000. So what does it mean that a directory has this size? At most 100,000. The total sizes of the directories above can be found as follows. The total size of the directory is this because it contains a single file. This directory IA has a total of this because it contains files FGH plus file I indirectly. Okay, so it is inside. So directory D has a total size of this. Okay, so each directory has the the file size of all the containing files. So we want to find the ones of a total size at most 100,000. So we want to find the ones that have less size. Okay, so given a tree, so then here we have to print, what is the sum of total sizes? Okay, sum sizes of directories with less than. Okay, we'll get to that later. So for now, we're going to have a tree is going to be a dictionary. This will be a comment that will have dirs, which will be a dictionary, and files, which will be also a dictionary. Okay, and the file, I want it to be a size, I guess, and a name. A file is going to be also a dictionary that will have a name and a size, right? Sorry, so files is a list of name. No, it's not a list, it's a dictionary. Okay. So for example, root equals this. 3, instead of 3, I guess we could be in a node, right? So the idea, we could use classes for this. I think it would make sense to have classes. Let's have a class. Class node. It has, or not, I don't know, maybe it's not necessary. Okay, so process. So we could assert, so let's say if I equals the length of lines, so we're in the end, we return. Then we should assert that lines I 0 equals a $sign. So we are always expecting to see, excuse me, a command in the beginning. Then if lines I dot starts with, for example, starts with this, then we need to read, we need to change the directory, right? Else else line must be ls, right? So in the past, before we did all of this, and it's always change directory, you always go up or down, and then you ls. So we could do an elif lines I equals this. Okay, and here we should assert false. So we're not, it's either this one or this one, right? So new dir equals lines I from which character. So it's from 0, 1, 2, 3, 4, 5. So from character 5 till the end, I think. This is the new dir we want to move to. And then we would do if new dir not in node dirs, then if we're moving to a directory that we haven't found out yet, I guess. Let's see again the input. Are we always listing before moving? It looks like so, but I'm not 100% sure. We could maybe moving to a dir not known. Yeah, this is not a problem. This is not necessarily a problem, but it could be. So what we should do is we should process I plus 1 if we are only advancing one line, and we are moving to node there's new dir. I think that's what we're doing. When there is an ls, we want to read the contents of this line. So let's say while lines, we can increment the I, and while lines I starts with. So while this is not a command, this is not a command, what we're going to do is we're going to read the output. And then it is if lines I starts with dir, if this starts with if this is a directory, then we append this file. So node dirs. If it is a directory, the dir D, let's call it, is lines I 0, 1, 2, 3, 4, right? So it's from 4 until the end. So D equals, and now we're creating a new directory. And this directory has dirs, which is an empty list, and files, which is an empty directory. Sorry, this is an empty directory. Else, so if it is not a directory, it is a file. So then the file, we have to split this line. So it will be size name equals lines I dot split. Size is an integer, so we need to convert it. And then what we do is node files with the name equals size. I think this makes sense. This root directory, in fact, should be an empty list of dirs and files, and we should call it with root, and we are processing line 0, so we are using lines as a global variable. So process line 0, and now we should print the root. I don't know if this will work, but let's see. Okay, starts with it's missing a T, and now there's a key error slash. Why? Because the first line we are seeing is this happening anywhere any other time? No. Maybe we can just remove this line, so we already know that we are in the root. Okay, assert false. Line 27. Print lines I. Okay, what is the line? CD. Okay, so it is either CD. Okay, no, but this Okay, I forgot to process recursively, right? So if you cd, you need to process the next line. And here you need to process the line I too, but with the same node. Okay, dot dot. We forgot to mention the dot dot. So the dot dot has a problem, which is that we're not keeping track of what is the parent node, right? So how can we do this? We're not keeping track of the parent node. Maybe there is an easier way, which is just storing all of the path for all the files, but I'm not sure yet if that is the way to go. How can we keep track of the parent node? We could do this recursively and returning, meaning you go up one. You go up one. So let's see. How could we do that? Instead of processing one line, what we should do is so if there's a change of directory, we need to process, and then we're back. So here we could say while I is less than the length of lines. Let's remove this assertion. So when we are changing a directory, what we are doing is if new dir equals dot dot, we return. If new directory not in no dirs, well, this is a bit weird, and then we go back here. And here what we should do is the end of this, we increase the I with 1. Let's see if this is right. So what we're doing here is, first of all, we are asserting that we always have a command. Then there's a cd. If there's a cd, we are either going up, in which case we return, or we are moving to a new directory which we don't know, or we move to a new directory which we do know, and then we change the command of the line and move to this node. If we are doing an ls, what we are doing is we are incrementing the I. So maybe it is here that we should increment the I. So we are incrementing the I while this is not a command. So we are just reading all of the output. If it's a dir, we are updating the node. If it's a file, we're updating the node, and then we are going to the next. And then this process, we don't really need to do this process because we are doing this iteratively, right? So we are increasing the one here, and we're increasing the one here. Let's see if this works. Okay, this falls in an infinite loop, seems. So let's print the I and the node. So where are we? Okay, line. Let's also print lines I, where we are getting stuck. Okay, it is an ls. So this ls, we should be increasing the I while not, well, it could be that we are just finishing. So it is while I less than the length of lines and, okay, no, this doesn't help. So what is the I here? 12, 13. We're just getting stuck here. 12, 13. Is the I decreasing for some reason? So let's print I lines I. Okay. And here, let's add some more debugging so we can identify this number here. Okay, so this is 11, 12, 13. So 12, 13, it says it's a file, and then we get back to 11. So this I is, for some reason, it is not being updated or something. Let's see. While I less than print I, of course this should be increased. So okay, here it is 14, and here then it is. Okay, sorry, this is wrong. I want to print this inside the loop. Loop. Now we need to do some debugging. Okay, so here there's loop 14, loop 10. I don't like the way this looks. I don't like why we have 14 and we have 10. I don't really understand. So here it is 13, here it is 14, loop 14, loop 10. Maybe I think we should start with the example. Maybe we are not formatting this correctly. I don't know. Let's see. Let's see what happens. Again, we follow an infinite loop. So let's see what is getting us in this loop. So here we see the E for this. It's clear that the I, we are not using the I correctly. So the I, this I is increasing here. Let's search for the I's. Okay, this I is increasing here. This I is increasing here. Print end loop. What is the value of I? So end loop 14, loop 14, end loop 11, loop 11, end loop 14, loop 14, end loop 11. So we are ending up with a lower I. I don't really understand what's going on here. So I is increasing, while I is less than the length of node lines. We're printing this, 13. I mean, we can do this differently. I still don't find what the issue is, but we could do this differently for sure. So we'd say next command equals the mean of the length of lines. So either this or how do we find the next command? So it is the next line. So I don't know what the issue is. I still don't understand what the issue is. So loop 14. it is cd dot dot. Oh, I know what the issue is that we are not updating the I when we process. So we have done this recursively, but now we are not updating the I. So here we should return, when we are returning, where is the return? We should return I. I is the new position that we need to, the need instruction that we need to process. So now, okay, now this is different. Okay, end loop. What is the problem? Well, I less than length of lines, and I is a known value. Okay, is there an empty return or something? End loop none. I guess we could here I don't know if this what this should be helpful for. Well, maybe. Okay, let's remove all of these extra commands for now. Maybe I don't want to do that. What is it? Line 15. Okay, sorry, I removed an extra line. Okay, so here we have all these directories. Now, let's see if this is correct. So here we have a root directory which has A. A has E directory, which doesn't have any directory, but has file I. Okay, this is correct. Has files F, G. It more or less looks fine, right? So here what we could have is, so after processing this tree, we could also, well, let's def count, let's put it here, count dirs with size greater, let's put a threshold here, which is this amount, 100,000. Okay, so how do we know the size of a current directory? So here what we could have is a node n, node. So the idea is, first, we compute the size for its node. So the first thing we need to do is compute the size. And the size would be, size is, first of all, it is 0, and then we sum all the files. So it is for file name s in node files dot items, because this is a dictionary, size is increased by s. Simpler way to do this is to sum the node files dot values. So this is the, I don't know what would happen if this is an empty value. So if what is the sum? So this dot values, what is this? Is an empty, and what is the sum of this? 0. Okay, I think this will work. So it is this, and then for each directory in node directories or dirs, I think I called it, size is increased by a recursive call of d. Now, what we're returning in this call is we could have a global name, a global variable. Maybe we will refactor this later, but is sol1 equals 0, right? So here we're returning the size. Sum size of files, sum size of directories. And here, finally, what we want to do is, if size is greater than threshold, no, if it is at most, so if it is less or equal the threshold, then we increment the solution. So here we should, let's say it count. Let's call it count for now. Count root, right? And this we are going to move here, and we're going to print this count. Well, we're going to print the solution one. Okay, count, blah, blah, blah. I changed the name, so this is count. Okay. String indices must be integers. Some node files values. String indices. Line 36. Print node. Let's see what this node is. It is this, dirs and files. What is the node files? It is this. And what is the node files values? It is this. So what is the issue here? You cannot sum this. Maybe these values are not exactly a list or something. So dict values. Yeah, we are summing this, so I don't understand. Line 36. String indices must be integers. Node files dot values. Print hello. Is this where this is really failing? Line 36. Okay, no. So, okay, node. Oh, so sorry. So node dirs dot items. This is a directory and a node, or let's call it n. So what we need to move is to n. Okay. Sol1 reference before assignment. So I think here we need to use global sol1 to make sure we're using this global variable. Okay. So now this is fixed. This is compiling. We're getting a count of 2. Let's see what the example says. In these examples, I can count files more than once. I don't know if it says what the example is doing. Maybe we can just run it with the input, and then we can, if this is wrong, which I expect it to be wrong, okay. Make sure you're using the full input data. There are some general tips on the about page. Subreddit UCAS40. Okay. So this is wrong. Let's try to analyze the example a bit further. Okay, it says 2. I'd like to see if this is true. So here, so this directory is less already, and this one here, it seems like there is only one directory, right? With size less than 100,000. There are 4 directories. /AD. These directories also contain files of various sizes. Since the disk is full, blah, blah, blah. Okay, so what we could print here, if we could add some debugging, and we could say print, so the node and the size. We could maybe print just the size, and maybe this is enough to find out. So this is 584, 94853, this is right. 239, this is right. And the outermost, it is 48, blah, blah, blah. Okay, so this is right. So the example, we are processing the example right. To begin, find all of the, oh, I didn't sum the sizes. That's what I got wrong. I need to sum the sizes. So, I did it completely wrong. So what, I didn't read the input. Fine, so what we want to do is we return the size and the number. So let's say accum equals 0, right? So this is what we have accumulated. So it would be, if size is less than the threshold, we accumulate. Do we need the accumulation or not? No, it is, what is the total sum of the sizes of these directories? Okay, no, we don't even need this. So what I think we need to do is just sum the size, not one, but the size. So in the example, well, let's submit this and then first submit and then think, right? Okay, it's too low, still too low. Oh, but because we are still reading the example. But this is wrong because the example only, oh yeah, the example has two, this one and this one. Okay, so I think we are doing it well, but we need to wait a little bit. So the idea is that we are summing the size to the solution if this size is less than the threshold. Okay, let's try to submit this again, 22 seconds. Okay, we were a bit slow today. I think we can improve the parsing also. Submit, and I'm still not sure if we got it right. Let's see, 5 seconds. Okay, gold star. Let's go for the second part. The blah 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 blah. Find the smallest directory that, if deleted, would free up enough space on the file system to run the update. Okay. What is the total size of that directory? Okay, so the total disk space available in the file system is this. To run update, you need to unused space of at least this. You need to find a directory that can delete and free up enough space to run the update. Okay, so I think we need to do some math still here. So for part 2, this is what is available. To run the update, you need unused space of at least this. So if I'm not good at counting the zeros. So this minus this. Okay, it's the opposite, right? Oh no, but the space is the disk is full. So there is 0 space. So you need unused space of at least this. This is what we need. I understand. So what we need to remove is, you need to find a directory you can delete that will free up enough space. Okay. Okay, no, but the total, and thus the total amount of used space is this. This means that the size of the unused space must currently be this, which isn't quite the blah, blah, blah. Okay, so return size. So this is the total size, or the root size is this. So the space needed is 7, this number, minus the root size. That is the space that is left. And we need whatever amount is left to get there. I don't know if I'm doing this math right. What did I call this variable? Space needed. Space needed. Let's see. Is this right? This is 3 million and we require 30 million. Okay, so we need 3 million. So we need to find the smallest directory that, if deleted, would free up this space. So sol2. So here it would be size plus equal blah blah blah. So the idea would be sol2 equals, let's add a bunch of zeros, right? So if, of course we forget about this, if size is larger than space needed and size is less than sol2, then sol2 equals the name of this directory, right? But we don't have the name of this directory. We could add it here, dir name, dir name. And the dir name, we need to give. So we should add in count2, we could say count2 root slash print sol2. Sorry. And we need to give this name when we call count, right? So instead of calling count n, we call n the. Okay, integer. Okay, this is not, yeah, sol2, and this is sol2 size. Okay, so this is sol2 has this name, sol2 size has the size. Sol2 size. We need to compare the sizes. So if, where is the problem? Size less than or equal the threshold. Well, we can forget about this threshold, of course. What is the problem? Line 43. Oh, because we're calling count instead of count 2. Okay. Sol2 size, sol2, sol2 size. Some recursivity we had to do in this problem. Okay, so the solution 2 is sol2 size. That is what we want. And it is this number. Gold star. Okay. This was a tough problem. Sorry. This was a tough problem. Okay, and I don't like the code we came up with at all. So we will need to do a lot of refactoring today. Okay. I think we should discount function. We could dir name, we could put it all together, right? The first and the second solutions we can do with one passing. Then we can probably remove the global variables. Using global variables is not usually the best idea. And here we used count n v, right? Even the threshold, well, doesn't need to be a parameter, right? So we call count root this sol1 sol2. What is this space needed? Okay, we computed this space needed here. Well, I'm going to backtrack. I'm going to remove this because it is clear that we needed okay, let's backtrack a little bit. Okay, dir name. I'm going to backtrack and leave it as it was. Okay, So here we say that the sol2 size, so the sol2 we don't need. It's clear. So what we need is the sol2 size. So here we can really remove this. What we don't need the dir name. We just need the size. So this is the size. Okay. The space needed. Okay. Here I think this should better be, space needed should be a variable, not something, not a global variable. So space needed, the sol2 size, we forget about it. Okay, dir name, space needed. Count to space needed. Okay, so here let's do an assertion. Sol2 equals this number. Let's do an assertion here. Sol1 equals this number. Today was a tough problem. It took me a lot of time. We had some debugging. We didn't have so many setbacks, but still, it was a tough problem. So now we are counting this. We are basically traversing the tree here, right? With count 2. What we are doing is we are traversing the tree and calculating the size of each directory. We could always... the code will be much simpler if we use a proper tree instead of using this root, dirs, files, and so on. I think I'm going to try to refactor the code to do this. And here, so this is the condition, if size is less than or equal to the threshold. So in the first case, this is what we wanted to do, and this is what the second thing we wanted to do, right? So one thing we can do now is compute sizes, right, of a node. So what we need to do, what we can do is extract this file. So first we sum the files. I think this is pretty explanatory. Then we sum the directories, and then we store it. So we would say node size equals size, return size. So if we compute the sizes of the root directory, then we would have, we could sum below threshold, which what we would do is forget about this. So what we would do is if node size is below or equal the threshold, then so the sum, the return value, we would sum this size. And then for n, or for dn in, what we're doing here, right? We then traverse all the children of this node. So the way of traversing these children of this node is we sum the sum below threshold of its children. So here we could even say child. Directory name, we don't really care. So we could say child in values. And then we return red. What we're doing here is we are summing below a given threshold. So we can forget about this sol1. So we're the sum is 0 in the beginning. Then if the node size for each, if the node size is less than the threshold, we sum this node size. We could say S equals the sum of sum below threshold child for child in this. So we first sum and then return. So then if s, return s. So now we are summing all the children values if they are below the threshold. And then we are summing the current node size if this is below the threshold. So we could say, we could even do this in a one-liner. So it could be node size if this, else 0, right? So we could even do it in a one-liner. I'm not sure if it is worth it. I think not really. Okay, and now this process 0 root, well, the process we need to do before. So first we process, then we compute the sizes, and then the solution 1 equals sum below threshold of root. Okay, count doesn't exist. Sorry. Line 34. Okay, compute sizes. Okay, root size is not defined. What is root size? Root size. So root size is root size now, because we have pre-computed all of the sizes. Okay, so now this assertion works. So now what we have done is we have simplified this sum below threshold, and then the second part is very similar. Instead of sum below threshold, is mine over threshold. So the minimum over the threshold. And the minimum over the threshold is, what we have to find is so the size is the mean over threshold. So let me see 1 second. So we can do it in a very similar way. Instead of doing the sum, we want to do the minimum, and the minimum will be let's do a simple way, and then we can do it in a one-liner if we want. So let's say s equals this number, right? So it would be for child in all of the children, x equals child threshold. If x, we could also start from here. Maybe it would make sense to start here rather than what we're doing. So I think that's what I'm going to do. So count 2, the size we already have I changed my mind again. So for its children, what we can do is x is blah, blah, blah. So if x is less than s, s equals x. We are computing the minimum here. If node size is larger or equal than the threshold, and node size is less than s, then s equals node size. Return s. I think this is more or less what we want to do. Let's check mean over threshold, root, space needed. Let's see if this assertion works. Yeah, it works. Okay, so we don't need any of these. We need the space needed. We need this. We don't need this. We don't need this. Okay, this is right. So we have this mean over threshold. I don't really like, well, these names of the variables. So this is part 1. This is part 2. Here we are read input. Here we compute the size of each node. Okay, what else can we do? What else can we do here? 1, 2, 3, 4, 5, 6, 7. I like this better. 2, 3, 4, 5, 6, 7. It's easier to follow. I don't know if you can, in C++, you can do something like this, but obviously not in Python. Okay. So, well, the elephant in the room, right, is this first function process. This is pretty atrocious. We need to do something with it. Then there's the compute sizes, which we can simplify, right? So we can also sum the compute sizes of n for n in node dirs dot values. Is that right? Sorry, we need to close the parentheses. Okay. Yeah, that is right. So we could even say, you know, I'm in general in favor of one-liners, but I would not say exactly being in favor is what I am, but let's see how this looks like. Okay, but this makes sense because this is just summing the values of the files, and then it's summing the compute sizes for n in node blah 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 values. However, I think there's a better way of doing this, which is just what we're doing is applying this function to all of the values, right? So we can map compute sizes to the node dirs values. So if I'm not mistaken, this is the same. It's even shorter. So this map, I like this map syntax a lot. I understand maybe not everyone understands it as easily as a list comprehension, but I think it is very convenient here. So we are summing this and this. However, we could also sum this and this, right? I think we need to this is not working. We need to sum. We cannot sum these two iterators. What we need to do, I guess, is we need to chain them. So we would need itertools.chain, which maybe is not necessary. So never mind. We can leave it like this. It is pretty compact. Here, node size equals. Okay. Okay, so this we have simplified this function a lot. Then sum below threshold. This one we can for sure simplify. This one I would also probably write it like this because it's easier to know how many zeros there are. So here we are summing sum below threshold. I like this word, this name better. So we are summing the dir sizes below a threshold. So I think that is a very self-explanatory name. It's long, but it's perfectly fine. And I think that is good. Here we could do the same. So we could map this function to all these values. Here we can have a comparison of the two. This, I guess this works, or maybe, oh, sorry, not without the child. So we that is the difference between the map and the list comprehension. We don't need this extra variable. So yeah, this is the same. You can see it is shorter than this, and for me, it is clearer. So we can summarize it like this. And then this sum, we could say dir size equals, here we have a node. This is not a node exactly. This is a directory. So, but anyway, so this is the dir size. Maybe it's a better name than S. So here we have the dir size, then mean over threshold. So what is this? This is the mean directory over this threshold. It's important that this threshold doesn't require this default value. And here I think we have an infinite value in math. So from math import inf, is that right? So I think it would be better to have this. So we could have, I don't know, even on top. So we could say from math import, inf. And here we can say this inf. Let's see if this works. Sorry, again. Yeah, it works. So what we're doing here, I think, can be simplified by saying well, again, we can here say dir size, which is more understandable word. Dir size. Dir size. Dir size, is that correct or not? No, this is not the dir size. This S value. This S value is something else. This is the return value, right? So here what we're doing is for each child, we're computing this number, and if this number is below, we return it. So this is the same as saying this is the minimum of S and this value. Is that right? No. Okay, so what is wrong here? So it's not the minimum of S. It is the minimum of, sorry. Yeah, it is, but this is S is this. Okay, so we have removed this X variable, which I didn't like at all. So here, this is the minimum of S and this, the child threshold. This could be done also with a list comprehension inside here, right? But maybe we don't need it. So, or maybe yes. So if we wanted to do this in a list comprehension, what we would do is let's put it up here. So S is the minimum of infinite and the minimum of a list, which is this, or maybe we don't even need a list. So this for child in all of these values. Okay, so let's see if this works. No, because this one is empty. So here, again, we could say, let's say if this is a list, what we can do is, this is the minimum of inf plus this. And here we could say, we could remove this. Is that right? What is wrong here? This. Okay. Okay, yeah, now this works. So the idea here is that this is the minimum of either infinite or all of these values. So the mean over threshold for child in nodeDirs.values. What is more understandable, this or this? I think it can be we could discuss which one is the minimum. Anyway, the solution then, it is either this S value or node size, as long as node size is larger than this threshold, right? So what we could do is, I'm thinking if we could put all of this in a single statement. So it would be something like node size if node size. So let's say, yeah, we could put it here, right? So it would be node size if the node size else inf. And we could return this value. Let's see if this works. What is this? Plus node. Oh, okay. Oh, which is unnecessary. Okay, it works. So let's break this down, right? This is it's a very compact way of implementing this. I could understand that it is not super clear, maybe, but what we're doing is, it's the minimum if of the node size, the current node size, if this node size is larger than the threshold, else infinity. So if the current node size is larger than this threshold, then we can take this into account. Otherwise, we take infinity. And then we add to this list, which is just a single element, we'll add the minimum for all of the children. So what we have then is we take the minimum of all these values. So this conditional here allows us to return infinity, ignore the nodes that don't have this size over the threshold. Okay, so this is, again, this is a one-liner. This is not a one-liner, but almost, because we are dir size plus node size. So this is just, we're summing this map. I think it's not necessary to put this inside here. And then we have the big function, right? I guess this, for example, this comment here, compute the size of each node, where we have this compute sizes, is not necessary. It is redundant. The read input is necessary because we have this process, which we don't know what process means, right? That's what we need to do now. We need to get rid of this process function. So I think there is a trick that we can do here. So here we have read all of the lines, but I think there's something better we can do. which is the following. If we open 7.in and we we read it, we have all of these commands, and we split it by $space, what happens is that we have every single instruction, be it ls, be it cd, in the beginning of the string. The problem is that the first one, we take the first one is empty, and that is the only problem, let's say, we have. So one thing we could do is we could edit this input to remove this $. If we do this, it would work. So what we can do is we could have commands equals to open split by $space. So here we read the input, right? We read the input. So these commands are interesting because then we will have an easier handling of these commands. So now we convert commands to 3, or let's say build 3. We're going to rename this to build 3. Again, let's remove this name. So build 3 is going to be this function. And how are we going to use it? Well, we are going to send the commands, and we're going to send the integer position we're using. So here, the root is the first node. So here, when we used root here, let's come here and put it here. And these are the commands. So we have these commands, 0 root. Now, we could discuss if the root is what we want, but what we're going to do is we're going to refactor this to use the commands. So these lines, this is going to be commands, right? Now, assertion of this, we can remove it. This no longer holds. And then we have two kinds of commands. If commands I starts with cd, then it's something. If commands I starts with ls, this is the other case. So what if it starts with cd? Well, then the new directory, it is the commands, let's call this cmd, commands I. We'll see if that's what we do, but if cmd starts with cd, then the new directory is cmd.split1. This is the second element, so we have cd and the directory name. If this new directory, it is this ... which means we go up. Okay, this is right. If not, we have already checked this if doesn't happen doesn't happen. So let's remove that for now. So what we do is we build the tree for commands I+1, no dirs, new dir. Instead of new dir, we're going to call it child, which makes more sense. It could be even, if we wanted, child dir, because we could have a child which is a file. It could be considered true. So then we have this ls, right? If cmd equals ls, what happens? And this is the part that I like the least. So we are iterating with this while and so on. This doesn't make any sense. In fact, I think this got wrongly formatted, right? There's something, this is wrong. But anyway, so this is more or less right, but this is pretty bad. So what happens with ls? With ls, what happens is that we have, first of all, this is not C, this is not equal, this is starts with, because what we have now is that the command includes the whole command. It will have all the lines after the ls. So what we have is for for row, let's call it row, in cmd dot split lines. We split lines and we ignore the first one because the first one is ls. So we take the rest and then we have well, so we have two parts always, right? We have a and b equals row dot split. So if a equals dir, then this is a directory, and then we need to create a new node, right? So this is the node dirs b, let's say, is what we have named it for now, and then we have else, this case here. So else we have size name is int a b, right? So this is b int name. We have seen that b is always the name, right? So this is always the name. So let's call it like that. And a is either the size or dir. So let's call it size dir. For now, size dir, name, of course, this is size and this is name. Well, what I was doing here, sorry, is that int size dir. And now we have it in a shorter way. So the thing is that with this for, what we have accomplished by having these commands is that we don't need to increase the I, because we're not reading line by line. We're reading command by command. So what we need to do is we need to increase I like this. So after the ls, we go to this next command, but we don't need to add this other plus ones. Let's see if this works. Hopefully it works. Yeah, it works. That's good, because otherwise I did a pretty big refactor here, and I didn't want to introduce a new bug. Okay, so here we are building the tree. Let's see if we can improve this in some way. So here we have a while, and we could we have a for with a range? Maybe yes, but it's not as easy, because here we want to increase this I many times. So it's not that easy. Let's think back to what we're doing, right? So what we're doing here, we're building a tree with these files, directories, size, and so on. There's one clear thing that we could do, which is use a class, of course, to build this tree, or we could use a name tuple. A name tuple is a simple way of creating a class. So it is from collections import name tuple. We could test it out here in this. How do we use the name tuple? So you have the type name and the field names. Oh, here's some good example, right? So this is kind of what we want to do. So what we could do here is we could have node is a, node. In fact, it's not a node. It's a node because it's a tree, but it's a directory in reality. So what we could have is a directory or a dir. A directory has dirs, has files, has a size, which we use later, and then, well, it can have a name, right? So if we did this, how would the code change? So here, instead of creating this, well, this directory is a I think it makes even more sense to have a class. So we would have an init function. Self, and here we would have self.dirs equals this, files equals this. So what we could do here is that let's see if this would work. So here what we would have is node dirs name equals node. That is one thing. The other thing that would change here is that this would be dirs and this would be file. Sorry, what did I do here? Files. And here we would have dirs. So that is the difference. Files, dirs, it's a big change. I'm not even sure if I'm going to stick with it or I'm just testing this out, right? But let's do something. I think we could just replace all the dirs with .dirs. Did this work? No. Oh, .s/ dirs. .dirs .size .files oh, sorry, .size, we need to do it again. This is a node. I'm still not sure if I want to stick with it. to be okay, it worked. Okay, so now it worked. What is interesting of having this class node? Well, one thing that is interesting is that we could implement all of these functions inside of it, right? So here we could say, imagine we said here build tree, and instead of using node, we used self, right? So this self, this node that we were using, it could be a self. So this is what usually is called object-oriented programming, right? You have classes, they have methods, you have objects and so on. So here we are building this tree given a set of commands. let's see, because I think I'm going to get rid of some stuff here. But here the point is that we could have root, and we could have root dot build tree commands blah 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 blah. So this would build the tree, and then I think everything should work. No, build tree. Okay, this is self dot build tree. I guess not self. It is not self. It is this one here. We need to build tree for this guy here, for this child. Okay, this works. So one thing we could do here, instead of using this I, we could say, okay, for I equals 0, I was thinking of returning the commands that are left, let's say. But maybe could we do that? It's tricky to modify a list while you are iterating through it. So the good thing about this, if we could build this function with the commands, and then we could do self.build tree commands 0, right? So we could say, okay, let's build a tree with the commands, and that's it. What is missing? Okay, the node. Well, the commands could be none, and if commands, we do this, right? So this, what we could accomplish with this thing is that we could even self.compute sizes, and this is something that we do ourselves. In this, instead of node, we have self. So we would be doing this as part of building the tree. Compute sizes. Yeah, this would be the well, this map, this is an interesting thing. We cannot use map. I think there is some kind of helper function to call this, to do this, but we can do we can just do a list comprehension. So it would be child.compute sizes for child in all of this. And I guess we can get rid also of this. So everything is fine. Everything is working. So now what we have, we build the tree using the commands or with the commands. So now we have this tree that we have built using those commands, build tree, compute sizes, and finally we have these functions, which we could also make as part of the class, right? So instead of node, we have this self, and then again the problem we have is that we need to call this as a method, right? So we need to call this child dot sum blah blah blah. Well, we can again remove this. So, but this is for child in, right? This is self, no, sorry, not self, but child dot blah 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 for child in this. So one thing we can do also, so this is the root, so this would be root dot and the same root dot. Got it. So the other thing that we could do here is we could have some kind of helper functions. So we could say, because we're having these dictionaries, which in reality maybe we don't even need. Well, maybe yes, because we can see the same things. If we see the same command, the same ls or the same cd happens many times, we may need it. But we could have some extra functions. So for example, we could have def children, let's say, that returns for self, that returns self.dirs.values or child dirs, right? So this could help us make this. So these values that we have here in many different places, self.childirs, maybe we should have to this name, right? Childirs. Let's see, where else are we using these values? In files.values. Well, we could maybe that. I think we want to replace childirs with childdirs. Sorry. I don't know. Maybe we just want to do cdirs, childdirs. Let's do it with a. I'm messing around here. So here, childdirs. Is this working? No, I got it wrong. I think we need this. Okay. Okay, now. So well, having this as an object, as a class, allows us to do this kind of things. So here is a problem. We read the input, we build the tree, we sum the directory sizes below threshold, and we get the mean directory size over threshold, right? The mean directory size over threshold. That is what we are really computing. So this name is definitely more understandable. Okay, well, as you can see, I love refactoring. What else can we refactor? What else can we refactor? Well, let's look at these functions again. So dir size equals the sum of this for each child. So for each child, we're calling this sum dir size. So one thing we could do, of course, is we could compute the size inside the building of the tree, but I don't like it because we may end up doing it. If we go through the same nodes many times, we may need to repeat it. So that is not a really good idea. Then we compute the sizes. We had this helper function. Then we have this sum dir sizes below threshold. Well, this threshold it is fixed from the statement. But I see here that we are not using it. Well, I mean, threshold, right? It's a bit verbose to do it twice, but well, I think it makes sense that we extract this magic value outside of this function. So this function is more general by doing this. So the dir size is this. If self.size is less than the threshold, the dir.size. We are not, this is wrong. So this is not the dir size. This is the sum of whatever value we're computing. So this is not a dir size. And this dir size is in fact also, what we could do here is self.size if self.size is less than the threshold, else 0 plus the sum, right? I think this is true. Yeah. And then we can return this. And we don't need to have this dir size or return value variable that we don't really need. So here what we're doing is we are summing our current size if it is under the threshold, or else we are summing 0 plus the sum of all the children. This is exactly the same thing that we're doing here, but except the difference is that instead of summing, we are doing the minimum. And here we're doing the minimum of, I don't know if this could be done with a tuple, or is it a tuple? No. No, because a tuple is in fact converted. It's not a tuple. It's a float. Okay, and here what we're doing is adding to this. We are taking the self.size if the size is over the threshold. So this is the opposite. Otherwise, it is infinity. And we are summing the mean dir size over threshold for each child that we have, right? So this is what we're doing. We could find map. So Python map. So we could find a way to see this, how to do a map with a method, but I think it's not needed. Okay, so I'm pretty happy with these two functions. I think this is handy. We could maybe, for simplicity, is it worth it for 3 times? Maybe not. So let's backtrack and remove it. It's just the same. And finally, we have this function for building the trees. So do we really want, do we want to improve this function in any way? I definitely don't like this CMD and this while, but I'm not sure if there is a better way to do this. I'm not really sure if there's a better way to do this. We could do it recursively. So instead of, so let's do this. Let's see if this works. So we take the first command, commands 0. So instead of this, of commands, well, we take the command 0. Let's see what happens. If we're doing this, we are increasing I plus 1 and returning 1. Instead of doing this, what we do is we return commands 1 till the end. Here we say commands equals these commands, we remove this I. And here what we do, so the point, I think we could even do, let's see if this works. So the idea for this star, if we have a list, let's say a list of 1, 2, 3, and if we do A star L equals L, now A has the first element and L has the rest. So the idea is that we take the first command, we take the rest as commands. So here we return the rest of the commands. Otherwise, we update them. And here we return commands. But instead of returning commands, we would say if len commands or if commands, we return self.build3 commands. So we have, instead of doing this iteratively, we are doing it recursively. So the point is, if there are more things, okay, this is not working. So let's see if we can see what is wrong here. So the commands here, we are taking the first one and keeping the rest. If we need to change directory, we return the previous commands. Here we take these commands from this build tree. So maybe return empty. So I'm not sure we're coming the end. Build tree. Okay, so what's wrong with these commands? I think the idea is good. So we take the commands, if blah, blah, blah. Instead of these commands, what we would do is like self.build3. So we build tree with what is left, right? After ls, we would do self.build3 with what is left. And this we can remove. Of course, this doesn't work. I don't know why. I don't really want to debug this much more. So I don't know what is the problem. Oh, sorry, commands. So what is the length of the commands? Okay, it seems like it is just returning, right? So what is the root? We haven't debugged this class yet, in fact. So this doesn't work. There's a good thing of a name tuple is that you would have some information. So we can do this. So I think, can we convert it to a dict? No, it's not terrible, but I think what is it called? If I'm not mistaken. Sorry, with a dot. Okay, no, okay, not callable. Is this right? Yeah. Okay, everything is empty. So something clearly is not working. So here we have this. Oh, wait. Not commands 0. That's what's wrong. Okay, so now we cannot unpack something. So we would do if commands, we do this, and even we do this, else we don't do anything. Build 3 commands, print cmd. Okay, we're doing some things here, like ls, change directory, ls, but when we're going up, then this fails. So when we're going up, but we don't need to return the commands, we need to return the self.build3 of the commands, right? Of the commands that are left. What is wrong here? DSSNR. So now we have something that is missing. I think I don't want to debug this much more. So I think I'm going back to the previous implementation with the eyes. Sorry, not this. I think I'm going back to this implementation, which worked. And even though I think that we could do better, a little bit better, let me try it once more. So the idea would be commands equals commands. Let's ignore the I for now. So if this is, we would then do self.build3. Not self, sorry. Not self, to the parent. So we need to, I think this is what was wrong before. So we need to return the commands. And here the commands are this, what these children gave me. And now we need to build 3 with these commands. And finally, and this is the same that we should do here. So, and so we are calling this recursively, and we're saying if commands equals an empty list, return. Let's see now. No. One argument I. Okay. Build 3. Blah, blah, blah. Let's remove this. 1, 2, 3. 1, 2, 3. 1, 2, 3. Cannot iterate if not commands. Maybe it's none. Okay, there's an assertion error. Well, I think now I do. So this is what I think would be the good implementation. But it's the same as before, the same problem as before. So when we do this, oh, okay, here we return the commands. So we return the commands. Okay, so I admit my defeat, and I'm going to leave it as it was. Today we already spent enough time with this. So this is the code I ended up with. I hope you enjoy it. I think we could, let's now comment the lessons we learned. Okay, what lessons did we learn today? Okay. First, one trick, as always, I always do the same thing. Let's put it as a multi-line string. So first of all, we edited the input. We are doing this almost every day to remove the first line and in the second line. Then we splitted the input with $space, which was helpful to divide the commands. So then the interesting thing here is that we used a class, the node class, which was helpful, and we implemented an init function. So this init function with an init function, this function is what is called a constructor in object-oriented programming. It had one argument, or optional argument, which was this list of commands, and that is one way we had to organize our code a little bit better. So instead of using dictionaries that we know that have the dirs or the files or the size keys, instead of using this dictionary that had some keys, we are using a class that we know that has some attributes. That's what it's called in object-oriented programming. Then for implementing this function, well, basically we need to use a bunch of recursivity today. Recursivity with what we could for, let's say, sorry, recursivity for tree traversal. That's what we're doing here. And then we used a bunch of, well, we used the from math import inf, which was interesting. We didn't use the name tuple in the end. So from math, we imported the infinite. We used sum, we used mean for getting sum, mean, map. I think in the end we didn't use map, but we used exclusively list comprehensions with list comprehensions. We also use many times the dot values method of dictionaries. That was interesting. I mean, not interesting, but it's a simpler way. If that's what you're interested in, only the values, that's what we did. And well, I think that's all more or less. I don't know if you guys learned anything else from this exercise. I think one thing that I'm not happy about is that I didn't get to refactor this function. And I'm debating myself whether to give it another try. I think I'm going to give it another try. I don't like to admit defeat with these things. So what we're doing is we're building a tree from a list of commands, right? Let's try to do this. So let's try to get rid of this I here. What we can do, instead of using this I, is we can just, let's say, instead of doing this, while len of commands, blah, 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 let's do it. While len of commands is greater than 0, right? So here, what we can do is commands. I want to use this star. I think this is a very nice hack. So what we can do is we get the first command. Okay, so now that we have the first command, what we can do, instead of returning I, we want to return the commands, which are the remaining commands. Okay, this we are not using anymore. And now what happens here? Well, what happens is that if you have to parse a child, what you do is you call it with a list of commands and you get back a list of the other commands. That happens either when you go back or when you finish. This I+1, we don't need it because this is what we're already doing when we are iterating this list of commands. And this return I think we don't need it either. So here, let's see if this works. No, int has no len. Okay, because we're returning. Let's return the commands. I don't know why we should return. Okay, now this is working. Okay, that is something. That is something because now we can get rid of this I, which we don't need anymore. Okay, we can get rid of this, and we can get rid of this. So instead of doing a big refactoring that like I was trying to do before, I'm doing it more bit by bit. Okay, so here we have this while, which is interesting. One thing we can do here is we could do this too. Another way of doing the same. So we're returning the commands, and here we have this and this in the end. Then we get back to the while. So what happens is that here we update the commands after we have parsed a child, and then we go back to the same loop, right? So what I wanted to do before is I wanted to do this recursively. So I want the self-build tree commands, and maybe what I forgot to do is the return here. And here instead of while, if length of commands equals 0, there are many ways of doing this. Let's return. So I think that is what I wanted to do. But no, I think this is really not right, what I'm trying to do. I think what I'm trying to do is not right. Because it's not exactly what I want to do. We could argue if we can do that here. So if length of commands greater than 0, self.build tree commands. So is this right? No. And if instead of if this is a while, then I enter. Oh, but here I have to do the commands equal, right? Again, the same error as before. So I guess this is just not right. But this is an improvement over what we had. So I like it. I like it. I still like it. So what we're doing here is just while we have commands, we run all of this. We take the current command and the remaining ones. If it's a change directory, we do this, which is we take the child directory, we return upwards if we are moving upwards in the tree. We build the tree of the child if we are moving down in the tree. And then if it's an ls, we're just adding some nodes. Okay, we're creating some nodes. Otherwise, we are, if it's a directory, it's one thing. If it's a file, it's another thing. Okay, now I'm pretty happy. At least I got to remove this I, which was bugging me. So that adds with this thing that we did here as another lesson we learned. So we used, sorry, we used this command here, which what it does is it takes the first element in the list and keeps a list with the rest. Okay, so I think I already showcased this in the IPython shell. Let me show that again. This is what we did, right? A, L. So A has, sorry, never mind. A has the first element, L has the rest of the elements. Okay, so well, the code I think looks pretty nice. Again, the constructor, we build the tree, compute the sizes, which we're doing calling from the constructor, and we part 1 and part 2. So that's all. I hope you enjoy it, and let's see you tomorrow.